according to my clock, it's time. Professor Hayashi, should we start?
Yes, please start.
Okay. So welcome to the first talk in the afternoon session. I gave the talk just before, so I'm sharing now Professor Nishimura's talk. So Professor Nishimura was trained at Nagoya University, and he's a professor there now in the informatics department, in the Department of Mathematical Informatics. His research interests include computational complexity and computing, and he's going to talk about a sort of quantum communication scenario in the cryptographic setting. So please start.
Thank you very much. First, I would like to thank the organizer for inviting me in this workshop. This talk is based on joint work with Akinori Kawachi, Mian University. Outline is the following. First, I would like to explain our setting, including previous work, SMP model and PSA model. After that, I explain result. Finally, I give an open problem. I consider the communication complexity, which is a very famous model in computational complexity. This model was introduced by Andrew Yao, who received Kyoto Prize last week. This model is very simple. There are two parties, Alice and Bob. Alice has input X and Bob has input Y. The aim is output fxy for some function. In this figure, both parties output the fxy, but if this output is not so long, then one of the party will output is okay. Now, these parties using communication channel, which is no error. Now, we consider how much we need send bits to compute fxy coordinately, which is the communication complexity of function f, is the length of bits communicate for computing f is in the best communication protocol. Here, usually in computational complexity, we consider the worst case on all input pair xy. So, for example, if all 0 and all 1, this communication is 10, and if 1n to 0n, this communication is 8, and blah, blah, blah. The most worst case we consider. And usually we fix the length of communication bit for all input. This communication complexity was introduced for a tool showing lower bound proof in computational complexity. For example, the one tuning machine has input to process this input. How much do we need computational time? Then we can use this model by cutting the tuning machine to part, this part and this part, and how much communication we need, like this. The most simplest setting in communication complexity is a so-called SMP model, simultaneous message passing model. This is, we have another third party called referee. who want to compute output fxy. But this guy has no input. Alice has x and Bob has y. Now, these guys does not communicate each other, just send to message to referee like this. Using this to message, referee must output correct answer. The communication complexity of F in this model is just the length of these bits in the best communication protocol. Now I explain a very simple case, parity function. This function is x, this is n-bit string, and y n-bit string. So I can write this. Now we consider the just parity. So all we adding all bit by module 2 and odd y. This is very simple. Just 2-bit communication protocol exists because just this can write 2 part n y I. Of course, this part mode 2 and this part mode 2. So this part for Alice's message, this part for the message, then just 2-bit protocol exists. On the other hand, another very simple function, equality, which is very famous function in communication complexity. This is also, the definition is simple, just n-bit string, 2 n-bit string is equal or not. Unfortunately, this has large communication complexity, 2n. Of course, this x and y just send. Then this guy can check x equal y. So upper bound is very trivial. This is trivial protocol. But lower bound is also 2n because this equation function can be written by communication matrix. This row has 2 to the n, and this column is all 2 to the n. This for Alice's input, and this part is Bob's input. Sorry, maybe I change this. This part Alice, and this part is Bob. Now, this component, EX, EQXY, this is equal 1, 0 if X equal 1. So the matrix is like this, diagonal unit matrix. Now we consider if this message is MX, then this guy send MX. If we fix this part MY, then this guy is sent MY. On the other hand, this is 0. So this and this must not equal. So to consider this, of course, this another part, but this must be not equal. Also, similar consideration, this must be not equal. So every this part mx and my must be different. So the length need for n, at least for n Alice, also for n Bob. So 2n is also lower bound. So basically, the lower bound reduced to distinguishability of input. Now, we can consider randomized setting in this model. In this case, Alice and Bob may use randomness. So referee do not always need to output correct answer, but need to do it with high probability, say probability 2/3. This case, we can consider the bounded error SMP complexity, which we can write RCC SMPF. On the other hand, randomness has two types. First is private randomness. In this case, Alice and Bob, also referee, must prepare randomness separately. On the other hand, public or shared randomness case, Alice and Bob has shared randomness. So in this case, we write the communication complexity using PUB. Now, we give also a very simple example for equality. Bounded error communication complexity using public randomness. Then constant communication complexity for equation function. Because we can consider shared randomness R, which is n bit string, which is chosen at random. Now we consider the inner product X and Y. This is the message for Alice. This means just Xi times Ry mod 2. Also, this guy send Yi times Ri mod 2. This guy check this 1 bit equal or not. Of course, X equal Y, then this guy always output 1. On the other hand, if X not equal Y, then probability 1/2, this guy output 0. So we can discriminate X equal Y or not by constant bit. Now we show the result by these 90 result. If we only consider private randomness, this case the communication complexity become square root n. So much gap, large gap for public randomness and private randomness. This talk, our result finally, our result is quantum case. So now I explain quantum SMP model. This case, Alice and Bob can send quantum bit. And of course, every party can use quantum computer. So I send this like this. Now we consider 3 types of QSMP model in bounded error case and exact case. Bounded error case, of course, no shared randomness. Also, no shared entanglement. So entanglement is particular quantum in quantum case. We can consider not only randomness, shared randomness case, but also shared entanglement case. So we have 3 types of variant. Also, exact case, we put subscript 0, so no error. Now, I explain the results in quantum case. If exact case, which means no error, quantum case is exactly same as classical case. So no advantage. On the other hand, if we consider shared entanglement, so this case, Alice and Bob has here shared entanglement like this. This case, we can reduce the communication complexity by half n, a kind of using dense coding, similar to dense coding. And most surprising difference is this randomized case and quantum case, no public randomness. As mentioned above, classical case, square root n. But quantum case, order log n, just order log n. So this gap is exponential gap. This paper is very famous using the quantum fingerprinting. So maybe some of you already know. Also, we can consider the multi-party case. This is just simply we can consider 2-party to k-party. Of course, this case trivial protocol is kn if all input has length n. Now we move to another model, PSM. PSM is a very special case of multi-party computation. Multi-party computation is we have several parties, and each party has its own input. The aim is compute F coordinately, but another restriction exists in this model, which is revealing nothing but F. So these guys compute function, but except for the functional value, no information is revealed. This restriction is very hard. So in fact, multi-party computation is not so easy. Of course, lower bound is more difficult to show. So we can consider the communication complexity of this model. But this question, how much is communication complexity of MPC, is an open problem. So Feige, Kilian, and Nauer in 1994 consider most simplest model, which is similar to SMP model. But we add security condition. This security condition is referee must not run any information but F. So from this output, R do not run anything except this value itself. This is the security condition. But for security condition, this figure is not sufficient because P1 to PK must mask the message. But this case, we cannot mask the message because this, now we consider again K equals 2 case. First party send MX, second party send MY. This case, we already see this must be different for compute equation function. But this and this same output. So R, if we get equal R, the input is X case, X and Y case. This case, the message is MX and MY. The output is 1. On the other hand, X prime and Y prime case also output 1, but the message is different. So we can discriminate these two. So referee has some information other than FX itself. So we need the shared randomness for considering security condition. So the K party has shared randomness R. Then we can mask the message. More formally, to define the security condition, we use the so-called simulator. The security condition is formally as follows. There is an algorithm called simulator that given fx output value itself as input. So simulator receive input as input xk. This is the output value. From this guy output all message, this M1 to MK. This means the message does not have any information other than input, this value itself. So by using this definition, we can define the security. Now, the communication complexity of PSM for function f is defined. Of course, we can consider the quantum case. This case, just we change the message to quantum message. Now, correctness, we can consider the perfect case. No error case and bounded error case, but in this talk, we consider the exact case. This communication complexity, we denote this PSM 0. 0 means no error. Of course, we can consider another quantum variant. This case, these guys share not only shared randomness, but entanglement. This is another model, so we can consider another variant. of communication complexity of PSQM model. Now I finish the setting of our this talk. Now I stop here.
Okay, so do we have questions about the setting? I just wondered if you could show the slide again about the kind of privacy requirement, the formal definition of security.
This?
Yeah. Yeah, so either of those is fine. I think I was just a little bit confused about what it means, what the simulator does. So it's you give it just the output of the referee, and then it produces the messages.
Yes.
What does that mean? What messages? Because you don't want it to produce. Oh, it produces the messages that like P1 sent to R and P2 sent to R.
Yes, yes, this message.
Ah, okay.
So
Oh no, I do understand now.
This message leaks the information about input, but the security condition which is prohibit. This means there is this algorithm called simulator because input is this. Then simulator can produce these message by this self itself. So this means this message does not have any information except this F.
Okay. Okay, thank you. Do we have any more questions?
Can I ask one question?
Yes.
Yeah. In the randomized communication complexity of the EQ problem.
Yeah.
Could you move to the slide?
Yes.
I couldn't understand why it is O1 in there. So for the
This slide, it's okay?
oh no, one more previous
No.
slide. Oh no, one more. I don't know. But yes, maybe this slide. Yes. Here, yes, I know that if X and Y equals, then it is only this protocol works perfectly. But I couldn't understand if X and Y are different, why it has a correct probability with
Okay.
probability 2/3. Yes.
Because X not Y means some I exist.
Yeah.
Xi not Yi.
Yeah.
So we consider this times Ri mod 2 this value. If
Yes.
this value is 0, then this message and this message equal. But this is not 0, then output 0.
Yeah. That's true.
Now
Yeah.
we have this value xi, xi not y.
Yeah.
Then this I part is equal 1. So
Yes, that's true. Yes.
Equal not maybe better to j. J not equal I case and j not equal I case. This part is 1 to R.
Yes.
So this is the
It's 0.
Ri, I think.
Yes, that's right. Yeah.
This is completely random.
Yeah.
Come from a shared randomness. So probability 1/2. This is not 0.
Oh yes. So the definition requires only 2/3 of the probability of.
Okay. This is simply we can repeat in parallel.
Yes, I see. Okay. Thank you very much.
Yeah.
Any more questions? Okay, then maybe we can proceed.
Okay.
So we're now at 2:30. So I think we have another 20 minutes.
Okay, thank you. Now, okay. We move to our result. But before I explain one example for a PSA model. After that, I explain more about in classical case. First, I would like to explain example PSM protocol for equality. This is two-party case. This we consider the n-bit string is correspond to the field element in size 2 to the n. Then P1, P2 has share R1, R2. R1 is non-zero field element, and R2 is field element in this field. And these guys send, this has X and this has Y. Now, the message is masked by this randomness using R1 X plus R2. This guy also M2 equal RY, R1 Y plus R2. Finally, R output 1, this message is same. Of course, this protocol communication complexity is 2n. Now, correctness is trivial because M1 equal M2, then, of course, X equal Y, then M1 equal M2. On the other hand, X not equal Y, then X not equal 0. So M1 M1 minus M2 is R1 X minus Y, and R2 is eliminate. So this guy is non-zero, and this guy is non-zero, so 0. On the other hand, security is a more we need consideration. These messages are
sorry, just if I may interrupt quickly, there's some background noise. If I think there's a couple of people who have the microphones open, could you please close them when you're not speaking? Thank you.
Okay. Maybe okay. Now we consider the security. Intuitively, the message is masked to random element. So it's okay. In particular, the referee has two cases. First, fxy, this guy output fxy. This is 1 if x equal y case. This case, the message is coming from M1, M2 is same because this equal this. So this mask means this is completely random bit. Of course, this is same. So the simulator output take random element and output the copy of this. This is simulator's algorithm. On the other hand, if this part is 0, then this is not. So this part is also not different. So this message must be different. So the simulator on input X 0, output different random element, and output this. This is the PSM protocol for equation function. So this is much complicated than no security case. No security case equation just send the x and y. Now I show the previous result on PSM, first upper bound case. Kirian-Nagoya in 1994 proposed a PSM model and show two-party PSM for any Boole function with exponential communication complexity. So important point is, for two-party case, with no security, 2n is trivial upper bound. But now we need security condition, so 2n is not trivial upper bound at all. These Kirian-Nagoya show the universal protocol for but exponential communication complexity is needed. After that, several people consider the specific function. For example, Ishii and Krishkushevitz, efficient. Efficient means polynomial n. K-party function, a PSM protocol for some restricted function. And also some specific function considered. On the other hand, lower bound is very difficult in this model. So there are a few results for lower bound. The most famous result, which is very recently, but in fact, there are unique result for very interesting result. This is about the 3n lower bound for two-party PSM for 2n input random function. So maybe you might consider the very weak lower bound. This gap is very huge. But in fact, this is the best result. Now we consider the quantum model. In our setting, we consider the correctness is always probability 1, and security is we have quantum algorithm, quantum simulator. Now, natural question is there any non-trivial lower bounds? Our first result is the Applebaum et al. Result can be extended to quantum case. So this lower bound can be extended to quantum case. But quantum case means our result, unfortunately, the shared part is randomness, not entanglement. So if this guy has shared entanglement, we don't know any lower bound. This argument is basically the quantum extension of the argument by Applebaum et al. But Applebaum et al. The result, the proof is based on combinatorial argument in communication complexity. So to adapt to quantum case, it's not so easy. So the proof is a little bit complicated. Now, I explain the second result. PSM model with shared entanglement. Now, this case, this K-party has shared entanglement. Now, another question is, shared entanglement case and shared randomness case is different or not? This is our second question. To give this our result, we see the SMP model case. SMP model was PSM with no security. This case, there is some problem such that shared entanglement is exponentially smaller than non-public randomness case. But this result, this problem is very artificial relation problem. Of course, this result is bounded error case, so most in this sense, this result is very good. But the problem is artificial, so this part is not good. Another result, there is a partial function such that entanglement case is exponentially smaller than a public randomness case. This is the problem itself is a little bit better, but still this is a partial function. It's not, and also the problem itself is a bit artificial. And another not good part is exact case. But the gap is exponential. This is good. Now, our second result. In fact, this result is not so difficult, so a kind of observation. This result is, there is a partial function such that PSM with shared entanglement is exponentially smaller than no shared randomness case. Of course, we consider the exact case. So in fact, shared randomness is no useful. So and this result is essentially come from the previous SMP model case. We use the so-called distributed Deutsch and Gyoza function. And another result, there is a total function, which has the SMP complexity is 2n, but shared entanglement case is n. So the gap is double. But this result is good point is very natural function, equation function. Of course, the bad point is exact case and not so much gap. But I would like to note this gap is the best gap in this setting, even in bounded error case. Now, our third result. This result is K-party result. We show some total function exists. This PSM communication complexity is Kn, with no entanglement. But if we have K party has shared entanglement, this function has communication complexity is Kn divided by 2. So again, this gap is twice, double. In fact, this function is natural extension, a kind of natural extension of equation function. This condition hold, then this generalized equation function is 1. This means x1 equal x11 to n bit string x11x, x2 equal x21 to x2n, like this. The K party has x n1 to x, k1 to kn. Now this condition means that just add by mod 2. So this part addition is 0. Also this part is addition 0. This is generalized equation function. To give this PSM protocol for this function, we use the cat state. In particular, we can see 2-bit string case, x11, x12, x21, x22. This case, basically, we use the EPR pair and applying xz depend on the first input, first bit is 1 and second bit is 1. Then if the input is same, then output is original state. And if the input is different, then we get the orthogonal state to this. But for security condition, we can randomize the input by using another shared randomness. So first, the party applying R by input and using the same protocol. This case, we can randomize these 3 different states by using this. So we cannot discriminate these 3. This is the basic idea. We can extend this idea to general N and K. Now finally, I would like to open problem. Our first result is this, non-trivial lower bound for a quantum case. But extension to shared randomness case is open. Also, bounded error case is open. And also, we can consider the relaxed security condition. So we consider the exact simulator, but we can also consider the approximate simulator. In fact, classical case considered the approximate simulator and obtained some result. So natural question is extend our result to this approximate simulator. And also, there are very few results even in classical case. So any lower bound for classical case is very good result, would be very good result. And our another second result and third result is the difference between shared entanglement and shared randomness case. Of course, this result also exact case. So bounded error case and Lux security case is open. And bigger gap for total function is also open, which is even no security case, SMP case. Finally, we have open problem, quantum communication complexity of PSM versus classical communication complexity PSM. Of course, no security condition, this two has exponential gap. So this PSM case, we to finding any exponential gap or some gap is very good result. And also, we can consider the quantum problem. So far, we consider only the classical input and output is classical function. But this function can be, we can consider the quantum case. For example, this input is quantum state. Output is, for example, this two state is close or not. This is another open problem. That's it. Thank you very much.
Thank you. Do we thank you for the nice, interesting talk. Do we have questions?
Yes, I have one question. So, could you show me again the your third result?
Third result. Yes.
Yes. This is somehow. And the protocol, your protocol generates, of course, k equals 2. Now I want to focus on k equals 2. In that case, you need to generate and maximal entangled state.
Yeah. Share entangled state. Yes.
So then you apply some unitary.
Yes.
And that each part send to their qubit.
Yes, yes.
Then that third party can distinguish that modulo sum of this one.
Yeah.
That method is somehow very similar to our paper in the today's first talk with Song.
Really? I am not here. I was not here.
Completely same. We essentially use that, but the purpose is private information retrieval. So in the case, so we need to hide some information, but maybe the security condition is completely different. But somehow using that technique, we can hide some information, but the third party can get some information. So I cannot remember what is the task in this case, in that simple case.
This simple case is the task is compute function equation. So these two
equation means x1 equal to
x1
equal 1 not.
Yes.
Equal 1.
x1 equal x2, 0, x1 not equal. This is the task. But, we, of course, we must keep security condition.
In the security condition is that each part have to keep the secret.
Yes. So this guy does not any information except the output itself. So we use the randomness here.
Indeed, in our case, it is a little bit different. Our protocol is a little bit different. So we only apply the Pauli operations on each qubit. So if the two Pauli operations are the same, then they are cancelled, but they are different, then the state is different. So like in your table, so if the two Pauli operations are it is 0, 0 is, for example, the identity, and 0, 0, 1 is X, and 1, 0 is Z, and this 1, 1 is XZ, is, and that, and so if these two Pauli operations of two parties are the same, then like in your table, we also have the maximally entangled state unchanged, like in the red ones. But if the two Pauli operations are applied, Pauli operations are different, then like in your table, the states are changed as other Bell states.
Yes.
So basically, the result is the same, but we don't. Our protocol don't use the randomness indeed. Yes, I think that's the difference. I think.
So sorry, I missed that. Why there is randomness? What is randomness?
So this is the shared entanglement.
Yes, of course.
And another randomness are this is the in fact 2-bit. This using A and B, this for masking the information. So first party, for example, this first consider calculate Rx. This guy also calculate Rx, R2. Then we run the protocol, this type of argument. So for consider this is x1 dash, x1 prime, and x prime. For this two input, we run this xz on register like this. So using this table.
So in our case, we don't apply this Rx. So instead of sending Rx, we send maybe the sum of the x1. In here, you apply the R dot x1, but we do the 1 dot x1, something like that. So, and in that case, the referee, I think it's a referee, the referee doesn't know the each of x1 and x2 because in the maximally entangled state, they are cancelled. So the only information is they are different or not. Maybe I think, yeah. That's a little bit different. That's a little difference from our protocol. But I think this is exactly, well, essentially these are similar protocol, I think.
Question I'm very confused because so local state is maximally mixed state. In that case, we don't need to R, even if you apply some unitary, player one apply some unitary, but still this state is maximally mixed. So then we don't need to R, I think.
No. So if we do not apply this, then if x1 equals 0, 1 and x2 equals 0, 0, then R get to this state. But this change to 1, 1, say, then output is, sorry, maybe.
Now the information
change to another state. So R can get information about this difference.
Partial information.
Yes. So we must hide this difference by using.
In the current situation, the requirement is also some information, no information leakage, even for somehow relationship between the two players.
Sorry.
So, sometimes now you mentioned you care about the case. Some correlation information for correlation might be leaked to third party. So you want to avoid that situation, then you apply R.
Can I just interject to say that it's 3 o'clock? So Professor Hayashi, do you think we should maybe continue this discussion later?
Yeah, okay.
Because I think the next talk is supposed to start now, right? Okay. So thank you very much for the very interesting talk again. And then I hand over to you as chair, right, for the next talk.
Okay. Who is the next?
I think it's me, right?
Man-Hong Yoon.
Yes.
Hello.
Yeah. Hi. Hello.
Yeah. Please start. Can you share the slide?
Yes. Let me share the slides.
Yeah.
I think it is here. Okay. Is it good?
Yeah. Perfect.
All right.
Please start.
Yeah. Thank you very much. And let me put my laser pointer. Yeah. Okay. Yeah. I would like to thank the organizer for having me to be involved in this workshop, which have been very diverse and very nice, and I've been enjoyed very much so far. My name is Man-Hong Yong, and I actually for this workshop, I think I actually initiated I think maybe in 2018, if I'm not wrong, or 19, and would be my first connection between SUSTech and Nagoya University. Actually, by that time, I think together with a few students, we visited Nagoya University and physically, and we had a really good time. And now things changes a lot since then. So I am very glad that we can still have such a connection over the internet. Hopefully, in the future, maybe when the COVID-19 thing is over, so we can have more physical meetings. So just a little bit introduction of myself. I did my bachelor degree in Hong Kong and master degree. So sorry, let me want to share my part of the screen over here, but it seems wait because I need to, because I cannot see all my slides. Okay, now I think I can. Okay, so this talk will be a little bit unusual because it's really based on my interests. Have been shifting a little bit over the course of my career. So I did my bachelor master degree in Hong Kong, and then I moved in to UIUC, studied a PhD in physics, and I moved to Harvard Department of Chemistry, and then I moved to Beijing after that, Tsinghua University, and then I moved to SUSTech, and then became a chief scientist at Huawei since 2018. So it looks like I am moving around, different places, but my overall goal of my career is still the same. So I would like to build a quantum computer, or at least involved in the building such a device. When I really started my career in Hong Kong, I didn't expect that such an opportunity would come fast. Actually, in the beginning I have no idea, whether I will even be able to build one at the end. After all, so then when I really start doing it in 2004 and 2009, and even in my postdoc time, I was a little bit pessimistic. Actually, when I worked in Tsinghua University, I thought maybe after getting tenure there, I would switch to some other fields. So that I really I did have some kind of force over at that time. But things just changes really fast after I think like 5-6 years ago. And so now I feel like things are not so far away. So thanks to the many people in the field working very hard to make this the hardware part the development really fast. So I'm pretty glad myself that I since been around different places in my career, that I accumulated some knowledge in physics, chemistry, and algorithms, complexity, and now start doing software. So this talk is more about my view or my thoughts about the current situation in quantum computing. And this talk is really not like a research talk we have seen so far. So I really would like to have some discussions about with experts here, with different fields here in this workshop. Maybe also we have a discussion session tomorrow, right? Panel session. But even for this talk, I would be, I welcome comments and discussions about the recent developments in quantum computing. And I think my view would be a little bit different from the views of you may have seen over the media, because it seems that we are getting from some media, it seems that we are going to have a quantum computer like next year or so. And actually, we still have a lot of challenges that we are. So this can only you can only really feel it or really understand it when you really get your hands dirty. You try to build a quantum system. So now recently I've been working with experimental groups very closely. So now I understand much better, what is going on. Previously when I was pure theorist, I was like, okay, give me this algorithm. Okay, so I will simplify it as much as possible, and then try to talk to experimentalists. Okay, usually experimentalists will tell me yes or no. We can do this or we can do that. But I had totally no idea why couldn't you do such a simple thing. And now, so since I go to the laboratory more often, so I start I really understand the underlying problems. I think this helps me a lot in really thinking about it. But of course, my view only represents more from the point of view in China, because we are not now we are not so and we don't get to know very much about what is happening really in the West, and in particular those latest developments in these quantum devices. I think we have to admit that China is a little bit left behind in terms of that, but we are working hard trying to do that. So this is like the like the beginning. And what points I think for most of us, what points are really to the quantum computing science or even quantum computing. So really it's about Moore's law, and everybody talks about Moore's law and quantum computing. But many people talk about the end of Moore's law, but not associated with quantum computing. Since I get to know about this more after I joined Huawei. It's because in our laboratory we are basically finding different ways to get around with the end of Moore's law. And so most people would believe that now is more or less over, but we keep improving. But I think the cost and the speed is slower than before. So we are talking about 7 nanometer, 3 nanometers, but we are not going to be like 1 angstrom, right? Because it gets to the atomic size. So at the end of as we are approaching the end of the Moore's law, we can we can start thinking about different ways to get around it. So now from my understanding, we can change different ways, at least 4 ways. So you can change the structure. For example, you can make it a distributed computing, or you can make it like a computing in memory, optoelectronic, or you can change the material. For example, now people are talking about carbon-based semiconductors or some even more exotic 2-dimensional materials. Maybe this can help, or maybe we can change algorithm. So since now we understand that there are many applications that if we tolerate a certain amount of errors, then we can, there's no need to make every step very precise. So this, for example, neural network or neuromorphic quantum, not quantum, just computing. Maybe there will, in the future, maybe there's a quantum neuromorphic computing. I don't know, because it's like a brain-inspired computing approach. So in quantum computing, we are really here. So we are trying to change the theory. Okay, so everybody, I think here we have lots of experts. I don't need to explain much, but yeah. So quantum computing is just one option, and I think in particularly we are not going to claim that quantum computing is to replace these things. So all of these four approaches, maybe they are not, they don't mean to replace the existing structure that we have, because already we can do something really fast, right? So there are many things we've been doing quite well. There's no need to change it. I think what is needed, for example, you say like specific applications like facial recognition, right? Natural language processing. Maybe we can use AI, but if we do some other ordinary things, we don't need to use complicated structures. Maybe we already will be sufficient. So this is the same for quantum computing. So this is like really one of the messages that I want to put it on the table, especially for students who maybe for new students in the field. Maybe they are so excited, they expect quantum computing will change everything, but probably not. I will explain. So this is like one of the messages that we really want to send out. So to get you to understand a little bit why the end of Moore's law, that we're going to have trouble. Of course, this is very elementary. I just mean for students who may not be familiar with all this. But of course, if you get to the atomic scale, so we only have individual electrons instead of currents. Of course, classical computing will fail. But what is perhaps even earlier, what will we see? Why the Moore's law will end even before the atomic scale? So it's because we have all these quantum effects when you shrink your scale to a very small scale. For example, if we consider a capacitor in classical physics, in textbook, maybe in general physics. So we are taught that, okay, so there are two pieces of metal, and if you put a voltage here, some of the electrons will go from one place to another place here. The reason why the electron get accumulated instead of jumping over there is because they don't have energy. They don't have enough energy to cross the energy barrier. So just like they treat, it's like classical picture that if you have energy that is larger than the kinetic energy you have, you're not able to jump over. You just bounce back, all right? So basically this is the same situation if you look at it from a classical picture. So therefore, from the classical theory, we should have a very stable current or voltage here. We should have a very stable signal, at least. So here, if you measure just the voltage, and so if you shrink the scale of such kind of devices to a microscopic scale, so then these electrons will behave like waves instead of classical particles. They have like wave function. And in quantum mechanics, we know that, so if you have a wave particle like this, so it's going to, it does not need to have the energy. It can be, you can have a much lower energy than the energy barrier, but you can at the same time cross over. So this is called quantum tunneling. Okay, so if you shrink this device over, so then the electrons will jump back and forth. And so in a pictorial way, it will look like this. Okay. So you get all the fluctuations, and you don't have a stable structure anymore. So this is the idea. So therefore, we have this quantum tunneling effect. Really is a negative effect somehow in making our device stable. But the whole point of quantum computing is exactly try to exploit such kind of effects to make better qubits, okay, quantum bits. So let me explain a little bit here. So yeah, I think it will be interesting to compare between classical bits and quantum bits. Actually, the classical bit is not that purely classical. It's also quantum mechanical in the physical layer, but in the logical layer, we see it is a classical bit. Anyway, so currently our classical bits are usually made of transistor, which is basically a structure involving semiconductors plus p-n junction. Okay, so all of these are quantum mechanical. so therefore, in some sense, we have been already have a quantum device, but at the logical level, we still operate. So these devices operate at a logical level as a classical devices. Okay, so why transistor is useful, or how it works? It's because for semiconductors, so usually we operate this device at room temperature, right? So at room temperature, semiconductors has a conductivity that is in between a conductor and insulator. It's just like its name implies. So when you but the advantage is that, or the interesting point is that you can dope such a semiconductors to turn into N-type or P-types. So difference is that, whether they have a positive or negative charge carriers. So, but if you put these N-type and P-type semiconductors together, so then there will be interesting internal structures they will form, and such a structure is called p-n junction. Okay, I won't go for all the semiconductor physics over here, but the interesting point is that the current becomes one-dimensional, unidirectional, and then you can you can based on such a property, you can build all these logical devices. Okay, so this is basically the idea of how you operate, how you basically have classical bits. Okay, for quantum bits or qubits, it has at least superficially you have a very close structures. For example, you basically use superconducting materials. At the moment, the most popular material is like aluminum. Okay, so at room temperature, it is a conductor, but usually we need to for superconducting qubits, we need to lower the temperature to near absolute zero, right? So at very low temperature, this superconducting material becomes the usual conductor becomes a superconductor, and so it becomes basically no resistance. Okay, so why is there no more resistance? It's because when you lower the temperature, the electrons inside the metal basically will form a kind of a molecule. So two electrons will form a molecule, a bosonic molecule, and this is like so if you want to break the molecules, you need to have put energy. So this is the reason why they are so stable. So these so-called copper pairs is very robust against imperfections and vibration of the lattice. So therefore, this is the reason why it in principle has a very low or close to zero resistance. Okay, so for such kind of materials, it will, for example, if you have a current, you will flow through forever, almost. So you will be very stable. But if you put a so-called Josephson junction, which is usually an oxide layer. Okay, so you just put an oxide layer and put two superconducting materials around, and these copper pairs will have quantum tunneling. Okay, so that's just the effect that we have seen in the previous slide, showing that it is really a bad thing about classical bits now becomes a good thing. Okay, so this is a very interesting result. So if you draw the energy diagram here, so we realize that for such kind of a ring, lowest energy will be like representing the current the current flowing clockwise and anti-clockwise. So therefore, for such kind of devices, so they're really you have a really superposition or tunneling between from clockwise to anti-clockwise and so back and forth. And at the end, the lowest energy is like a superposition. So which means that you have both clockwise electrons and anti-clockwise electrons in the same time. And this is basically the idea of quantum superposition. And in some sense, some people call it Schrödinger cat, or at least small scale Schrödinger cat, because there's really a 10 to the 19 electron pairs flowing around. So it's like still a very large amount of microscopic superposition. Okay, so these are the summary that I will probably skip it because it's like popular science, and also quantum mechanics. I will also skip it. I will just comment that the experiment of Schrödinger cat is very analogous to the idea of quantum operation. It's not exactly the same, but I would say it's quite close to what we know about the CNOT operation, right? So if of course, okay, so there's a different, always different, but I would say just similar idea. So you have a small system and you want to control the superposition of larger system. So if you have a ground state, the cat will be alive, it's like 0-0. If it is excited state, the cat will die, then it's like a 1-1. Okay, it's similar. Of course, your photon goes to some other places around, but I think it's getting very close to something like a CNOT. So therefore, from my point of view, I would say Schrödinger probably is one of the first guys who has or physicists who already has some kind of a quantum computing idea, even in this famous Schrödinger cat experiment. And what is really needed right now is to think about how to create such a box, right? So the box is almost like a how do we it's like quantum computer already. So if internal devices and together with the box, if we can do it, and basically a built-in quantum computer. So it's the same thing right now. Okay, so there are many explanations of what superposition is, and I just say that we don't bother try to explain try to find an explanation. It's just up to individuals' interest, right? Everybody may have their own idea, but it's just a mystery. Okay, so just to get you some idea, everybody knows that it is our Hilbert space is growing exponentially. Here, I just want to put some number so that you get some idea about we are really facing this huge Hilbert space already. So with like a 20 to 30 qubits, so of course we already have can easily, even in China, we can easily produce such amount of a number of qubits. So this the computational Hilbert space is equivalent to a laptop computer. And if you have a number like 50 qubits, so already you need to for many tasks you need to use a superconductor for computing. So therefore, right now we are really at the age of a Hilbert space that is sufficient large enough to really do something interesting. So this is really the very exciting time that when I first start my career in quantum computing, I never thought that the time can arrive so early, because when I was still a postdoc time, we are still talking about 3 to 5 qubits. We are thinking about such kind of small number of qubits, but now it's really very fast development. So I created I asked my colleague to create a slide showing just to give you some idea or impression, why quantum computing is amazing, or where does the computing power come from. So like what I just mentioned, if you have like 20 qubits, so it is like the computational space at least is equivalent to the memory size of a laptop. So therefore, if you just shine some light on a array of 20 qubits, you're already actually doing a huge matrix multiplications in this huge space. Okay, so this is really the what is really happening mathematically. So left hand side is like physically, the right hand side is like mathematically. Okay, so of course, we now have like more than 50 qubits, right? So the right hand side, the qubit space is even larger that I cannot really draw on a PowerPoint slides. Okay, so I just give you some impression, that we really have a very powerful device in principle now. So the question is, how do we use it? This is really the question that I've been thinking about. This I don't need to explain much because everybody knows about what quantum computing. I just invented an equation by myself. So what quantum computing really is, it basically is still is a classical computing plus some features in quantum mechanics. Okay, so this is what really quantum computing is. And as you know, we have in the beginning we have this source algorithm, and with that, even though we don't even have a quantum computer right now, or we don't have a very clear plan when we'll have a quantum computer, but already people start working on post-quantum cryptography. Okay, so people are worried that in the future maybe my information here will be disclosed, maybe for some families, for some regime, I don't know, for some countries, maybe these secret documents has to be encrypted more than 50 years. So then they will be in trouble. Okay, and even like like Bitcoins, right? So this will be also dangerous if you don't change it in the future. It will all be cracked. Will all be cracked by quantum computer. Okay. So with that, so I think we can pause a little bit and ask the question. So when will quantum computers replace classical computer? So this is a very common question that I encountered over in many talks. So therefore I put it in the slide so that I answered it before people ask such a question. So I also implied it in the beginning of my talk. We are not going to have replace classical computers, at least I think in the near future, or in a very not so far away future. We are not going to use all quantum computers. So this is simply wrong. So the reason is quite simple. Even though we know that quantum computer, if you have quantum computer, then you can really have impact on many industries. Okay, in principle, I think so. This although we have we have problems with the lack of practical algorithms that I will show you later. But now let's talk about the logic. So why quantum computer will not replace classical computer? So this is something very simple. Okay. Some people talk about it. I just make it more explicit by showing the slides. Okay, so it could be quite confusing because in the textbook or in some rather theoretical papers in computer science in particular, we know that quantum computer or quantum computation is a generalization of classical computation. So what it means is that I can simulate any classical operations by quantum gates. Okay, so therefore classical I can do any classical computation with a quantum computer if we want. Okay, so this is true. So this is I'm not saying it's wrong, but it's not practical. Okay, so even though mathematically or in theory they are like have a subset relationship, but in practice they are not equivalent. So think about think about the analogy like an airplane and car. Okay, so suppose we only have a car, and now we are building a plane. So in principle, a plane you can use a plane as a car if you want, but it is not so good for short distance. It is still you know, if you want to drive from 10 kilometers or a little further away, it is very useful, right, if you're driving a car. But if you say, okay, I want to drive a plane for relatively short distance, then it is not so good because it is turning around is slower with a plane, right? So the point is that, you know, we really want to use a quantum computer to do something that is not possible by classical computer. Okay, so this will be, I think, will be the right way to think about what is going to happen in the near future or not so distant future. So really, you know, we need to find an application. You know, when do we really need a quantum computer? Okay, so just example, like previously Shor's algorithm, maybe factoring numbers is one of the examples that we should think about. Although it requires like general quantum computers that we are going to discuss about it, because we also think that general quantum computer is a very is still very challenging. I mean, we should think about something more reachable, maybe within 3 to 5 years. Okay, so as a kind of a summary of the roadmap, that I think the EU roadmap is quite accurate so far. So in the beginning, I think you should look at the bottom. So this is really the time I was a student and postdoc. You know, I have like have seen like qubits like less than 10 qubits, and we were, you know, trying to think about how to what application we can use them for. But by the time it's only for publications, only for publishing papers, and we are very excited to learn that in 2019. The Google's team claimed that they reached the status of quantum supremacy or quantum advantage, okay, by demonstrating an experiment with a quantum chip with 53 qubits and demonstrating a sampling problem that is out of reach of classical computer. Okay, so since 2019, I think many teams, including us, trying to check or trying to challenge Google's claim, whether it is correct or wrong. Maybe we just don't have a smart enough algorithms, right? So a classical algorithm. Google in Google's paper, they have lots of comparisons. Okay, so they have lots of simulations, but maybe they just don't didn't do it in the most smart way. And it is true that over the couple years, many works have such an improvement that is getting, I think, is getting close to be successful in challenging Google's claim. I think maybe within a year or two, maybe even shorter time. I think we will. We are also working on it. We were able to show that it is indeed possible to challenge Google's claim that we can use classical computer to simulate this chip. Okay, but I would not be be disappointed because this result was in 2019. I think Google, maybe now they have better chips, they can have better fidelities, and this will increase significantly the challenge in in challenging this quantum supremacy. So therefore, I think this is it is now pretty safe to claim that, or to believe that we now have a quantum chips that can perform certain tasks that is cannot be reached by classical computer. Although, of course, this is the point is the problem is that this task has no practical applications. People thought about, okay, maybe you can use it here and there, but I don't think that is practical. I think so far we really want to have something really solve some practical problems. I think we have not reached the first step. Okay, or according to roadmap, that we need to have a gate-based quantum computer demonstrating practical utility. But now I would compare the situation like like right the time of in 1900. Okay, how to pronounce 1000 1900? I don't know how to pronounce it. Okay, so like 100 more than 100 years ago. So by that time, when the Wright brothers first demonstrated, they can build so this is a prototype of kind of empowered aircraft, right? I think if I remember correctly, so this thing can be in the air, can be on the air for 1 minute or so. So if you start at a rather top hill, and then maybe you can slide over. Okay. And by that time, so I think by the time I actually looked from Wikipedia, and at the same time, people did have reasonable car. Okay, it's a gasoline powered car. They can take people to go from fairly distant away. So by that time, you can look at this guy. What do they think when they look at Wright's aircraft? Maybe it is exactly the same time, same situation that how we look at ships like this. Okay, so I think the conclusion is that if you have underestimation or overestimation, they are both wrong. Right. So we are not going to have a quantum computer next year or 2 years later. It's not. There's no reason to believe that we can have a universal quantum computer replacing every classical computer with that short distance. Okay, it is also wrong, I think, or underestimated if you think these are rubbish. These are hype. These are we are still far away. I think somewhere in the middle would be most close to what will happen. Okay, so this is like my analogy. So I think as a person working on this field for like 20 years, I'm very excited for myself, because we really can see something really the hope of getting something practical out of this the pure concept starting from 1980s, right? So this is like so if we go back to look at the trend, it is reasonable to believe that maybe by the end of this year or maybe next year, we are going to have like 100 qubits. We won't be surprised to see such a development, because there's no like obstacle in looking at the number of qubits becomes a bottleneck. Of course, I'm talking about good qubits instead of like a qubits that has a reasonable small arrays. Okay, so now people know that. So we all talk about NISQ, right? So it is like so of course when I was a postdoc already, we think we just don't have this term, but we already expected such kind of situation will happen for a long time. So what is happening is that we have a relative noisy case that is maybe the area is like large, maybe above or below air threshold, maybe. So so the number of qubits maybe like between 50 to 1,000 maybe. So this is very crude. I also just collect this data from the talks over the internet. I think so. These are representing, in some sense, a common consensus in the field. So maybe within 5 years, we will really be able to do error correction in a reasonable way. So now, of course, we can just do some demonstration, but maybe within 5 years, we can really see that error correction can really build a reasonable logical qubits. Okay, and then we will start moving along, and then be able to do fault-tolerant quantum computer. But this is really far away. Okay, so I personally am not that interested in this part. I am more interested in really finding out what is going to happen with this NISQ without error correction. What are we going to have? People. So this, I don't know who start this, but now it seems that there's 3 major applications or directions in NIXQs. Like the first one is quantum simulation. Second is like combinatorial optimization, and third is like machine learning. Okay, so again, so I like to emphasize that. So starting from the 1935 and over the course of time, like in the 80s, 90s, and so this is like the beginning. So we start to have a theory that is real enough. We don't understand, and in the middle, we start to make this thing to make a reasonable application, thinking about theoretical problems of this quantum theory in the context of computation. And starting from 2010, I think we really entered the regime of quantum computer engineering, or the software, or both software and hardware engineering. So we are really in this region now. So there's so many. So since I really joined Huawei, so I really want to build a quantum computer, I encountered many engineering problems. Okay, so this is like so let me see. So my time is running out. It's so fast. Sorry, I thought I should stop early. So I will go for this really quick, and then leave some. Maybe we should have some time for discussions. So this is like the algorithm like I produced a couple years ago about the history of quantum algorithms. And so the point is that we have many interesting algorithms developed before year 2000. Okay, so all of our reasonable or inferential algorithms were developed before year 2000, which is basically by the time I start work as a student working on it. So this is kind of a disappointing part. It's not this comment I actually took it from my paper, the title paper of Peter Shor published in 2003, and then Shor believed that or complained that why haven't more quantum algorithms refined? Okay, so and I think so after a few years later, we have this now it's kind of popular algorithm called HHL algorithm in 2009. But as you agree, as most of you agree, that HHL algorithm is a kind of a what is called cocktail algorithm that you put stuff together, and then it's like an application, right? It's a new total, right, relatively. So and this basically is inspired by AI applications, and couple years and maybe a few years later, so we are now more interested in some sort of a variational algorithms that I was fortunate enough to be one of the inventors or pioneers in this area. So for example, we have a VQE, QA, many variants now we have seen. So these are, I think the interesting developments based on the influence of external force. So in the beginning, we have in the field, we can only have a imagination of mathematics, what will happen. But now we are as we getting closer and closer to something useful, we have really practical, more algorithms that looks very different from what we have in a textbook. Okay. Anyway, so this I think I will maybe discuss one more concept, and I will see if we can leave some room for discussion. So we are talking about universal quantum computer and dedicated quantum computer. And universal computer is like textbook computer, and dedicated quantum computer is really something we are doing now. Okay, so the problem right now we have is that when we can only run so-called shallow circuits, right? So because of the decoherence time, problem like this, and so in order to build a universal quantum computer, so what we have to do is to make this line to be very flat. So keep maintaining our computing power as much as possible by error correction, for example. So this is very difficult. And the idea of dedicated quantum computer is really try to obtain the computing power So before it decays, okay. So this is the idea, and then you use it many times. Okay, so this is the kind of the new way of designing quantum algorithms instead of the old way that you want to maintain this curve all the way until the end of the algorithm. But now, so what we are having right now, so all of the algorithms basically it's like this. So you will use quantum computer or quantum chip to just produce a small portion of the problem, and then use classical computer to combine them and then try to extract them. And this is really the why, if you look at the VQE algorithm, now you think it's very trivial, but at the time of 2013, this is already a very brave step, because there's no complexity proof. Okay, so it's only just an idea, and then we use experiment to demonstrate that, and then now people think that maybe it's very close to AI, and then so it cannot be explained, but somehow it works. So okay, sorry. So this would be my last information slides. Okay. So the situation is now like this. So for the right hand side is mostly for universal quantum computer. So if we have this guaranteed this amount of good qubits, sufficiently good qubits, then we are guaranteed to be able to produce some useful, interesting quantum algorithms that is stronger or faster, have more computing power than classical computer. Okay, although Grover is kind of marginal, right? So we have HHL and so on and stuff like that. And so now the problem with NISQ is that we have these three directions. We don't know which one is will give us or will be the first to give us some kind of advantage that can go beyond this line. And what we are seeing right now is all our attempts are like below this line. So this is a problem. Okay, the problem of quantum quantum computing is that so we really need to find find some cases that is beyond this line. This power more powerful than classical computer, and also useful. Okay, so maybe yeah. Okay, maybe I'll just skip. So I don't explain VQE, and basically this is more or less the end. So I have so now if you want to make this happen, then other than the publications, we still need to do a lot of this hard work. So this is the reason why I did in this talk I didn't talk about any of my recent paper, because I published much less than before. So now I spend much of my time trying to figure out how to make this all the blocks, how do we put them together and make something really works. So with that, so actually I have many things I did in Huawei. So we are upgrading our hardware system, a software system. We call it HiQ, and then now it's 3.0, and it's now like capable of doing lots of interesting stuff. Maybe I talked too much in the beginning, so now I didn't have time to tell you much about the features of our system. But you're welcome to go to our website of Huawei, and then we also have this. Do I have the? Yeah, I think we have this. Sorry, we have this open source software, so that you can go to GitT. So we put all our software over there. Okay, so I think that's it. So thank you very much for your attention.
Thank you. Thank you. Nice introductory talk. Do you have any question and comment?
So I have one question. You make some table. In that table, you list up several algorithms. Among that algorithm, you write down, yes, Shua and Grover and Suzuki Torotta HHL, but I cannot find Suzuki Torotta. Somehow only some decomposition, not algorithm. Algorithm.
Well, Yeah, maybe I should put a SAW as well, cephaloi as well. So maybe I missed that. Yeah. So basically everybody knows about Shotsuki and Chotter, basically mathematical expansion. But I think cephaloi actually published in his science paper showing how this mathematical trick can be turned into a rather simple algorithm of simulating quantum dynamics. Yeah. I hope that you know what I mean. So, but yeah.
Using Suzuki Toyota decomposition, we can make some good simulation.
Yes, that is like I don't know, 2000 cephaloi has this science paper. Yeah.
Oh, I see. Okay, I understand.
Or maybe this one. Sorry, so maybe this one. Yeah, I actually did give some credit to cephaloi here. Yeah. So I put it as Suzuki Chotter's law.
Oh, okay.
Another comment and question.
Hi, Manhong, it's Oscar. Just you mentioned the Bitcoin things. So is it actually, have you looked at that, whether quantum computers can crack Bitcoin?
Oh yeah, thank you very much for the question, Oscar. So actually, I'm not so familiar with this blockchain technology, but I recently I met a friend in Tsinghua University, and I actually asked him. Okay, he did told me that Bitcoin will be cracked if you keep the same structure according to him.
Okay, yeah, I haven't
It's
studied
all based on RSA.
Okay.
Of course, he commented. Of course, we can change it. Change the current Bitcoin cryptographic method, but you need to have everybody agrees on it. So this is the hard part. So it's like decentralized community. You need to everybody change it and agree the whole structure and things like that. It's kind of challenging. It's like we have to move to a new coin structure. Yeah, I don't know. Maybe it had already happened a few times before. I don't know.
Yeah, and I think people talk about elliptical curves in the context of Bitcoin as well, which I don't know whether quantum computers can crack.
Yeah, I will expect that it will cost even more energy. Yeah. I think the problem is like energy. Yeah, energy cost.
Yeah, Bitcoin seems quite bad in that sense. They should modify how they make the coins. Okay, thanks.
Any other comment?
Another one is, I always forget about this, but with the Google thing, what was so this is boson sampling, right? And what is the status of error and error correction there?
Let me get to that point. Let me see. Where is it? Yeah. So Google's result has nothing to do with boson sampling. Okay. So it's a programmable 53 qubits superconducting circuit, and so of course the task is also sampling, but with qubits instead of boson.
Oh, right, it's a random circuit sampling thing. But and do they? What is the error thing? Are they, because it's not error corrected, right?
Not error corrected at all. So so the fidelity is something like 0.02. It looks very small, but if you want to do say classical computer to produce this same amount of fidelity, is still very difficult. We expect to require like 100 GPUs or things like that. Might be possible, but currently it's still the quantum chips is only 50 qubits, and then it took like 200 seconds, and maybe we need to have like 100 GPUs and with 3 to 4 hours, just some things like that on a scale. I think the most optimistic estimation.
Okay. Cool. Thank you.
Any other comment or question?
Oh, can I ask a question?
Please.
Yes. So as a researcher in theory, I always wondered when this real universal quantum computer will be realized. So, but you have many experience in physics and chemistry and experiments. So how do you expect the universal computation? How much time do you need to have a universal quantum computer?
Yeah, thank you for the question. Actually, I have this. So okay, on the table, I put a question mark here. I said like 10 years, but my view answer is like let's talk about it 10 years later. But yeah, so far, people talk about maybe within 5 years later we will be able to see really real error corrected qubits that really real logical qubits. Maybe, yeah, and then we should move on. And it's really hard to say, when we are going to have a real quantum general fault tolerant quantum computer. But actually, my main concern is that why do we really need it? Because if you look at the algorithms we have so far, so source algorithm would not be useful anymore because people change their encryption, and then Grover's algorithm so only give you a quadratic speed up, and so you need to build all these strange oracles and stuff like that. And then quantum dynamics, maybe we can do some physics like solving dynamic questions, but I don't know. AI is still far away. So I think if we really want to build a universal quantum computer, we really need to have a even more practical algorithm, I would say. So more it's same we need to have more like Shor level quantum algorithms that is to really justify why we want to just do that.
Okay. Yeah. Thanks. So is there some specific part that Huawei is concentrating on, for example, in specific algorithm or?
Yes, we're working on both three directions, like VQE, QAOA, and QNN. And I personally would believe that maybe QAOA would be closer to finding these practical applications. The reason is that for VQE, the final state usually is a superposition state that you really need to maintain the coherence, and also for problems like quantum chemistry, you need to be able to reach the so-called chemical accuracy, which seems to be contradictory because we are talking about NISQ. We don't talk about we don't do error corrections, but most of people now working on molecular structure, that usually requires chemical accuracy. So this is very challenging for quantum chemistry. Maybe for other simulation like Hubble model or whatever model, maybe this will be useful. But then we end up having a simulator like this. So of course this now, especially in China, development is very fast. For QAOA, because we can always perform measurement and got each bit string will give you some answer, and then I think this seems to be much easier than VQE, and there are lots of applications for QAOA like combinatorial optimization problems. So I personally think that maybe QAOA will be really the first winner in demonstrating the quantum computational advantage.
Yeah. Thank you very much.
Okay, now time is running up. Thank you very much again.
Okay, thank you very much.
Yeah, now I pass the chair to you.
So now I am the chair?
Yeah.
Okay, sorry. So I didn't expect that. So who is next? Okay, maybe I just say, let's get started. Okay, now it's exactly 4 p.m. So we have really good time control, and let's welcome Professor. Forgive me if I pronounce your name wrong. Let go. Yeah.
Yes, exactly. Just do this. Okay. So can I start? Is it okay?
Yeah, please go ahead.
Yeah, thank you. Okay, so I will talk about some recent work about quantum communication complexity of distribution testing. So it's a joint work with Alexander Belovs from the University of Latvia. Arturo Castellanos was one of my students at Kyoto University, now he's working in France. Guillaume Malot from the University of Paris, and Alexander Cherstov from UCLA. And the paper is available on the archive here. Okay, so I will explain first the notion of classical distributed testing. So classical distributed testing can be seen as a special case of a classical learning theory, which has been very popular in the past 20 years. So we consider two probability distribution, P and Q, so discrete probability distribution over the universe 1n, so n elements. And we assume that we don't know the probability distribution P and Q, but we are given access to a limited number of samples. And one sample, for example, for P will be I with some probability Pi. So when you ask for one sample, you get I with probability Pi for each possible values of I. And the same for Q. And you want to, given your samples, to decide whether the distribution satisfies some property or are far from satisfying the property. So I will not give a general definition of the notion of property and far from satisfying the property. I will rather describe exactly the properties we will consider today. This is closeness testing. So there are two versions depending on the norm we are considering. So I will start with the first one, the L1 norm version. So your task is to decide if P and Q are equal, so the same distribution, or if the distance between P and Q is at least epsilon, where epsilon is a parameter. And for evaluating the distance, we are considering the norm 1, okay, so defined like this. And the L2 norm version is exactly the same, but we are taking the L2 norm instead of the L1. And an important point here is that we never consider the case where the distance is strictly larger than 0 and strictly smaller than epsilon. Okay? So we assume that the input satisfies one of these promises. Either the distance is 0, so they are the same, or the distance is at least epsilon. We never consider input that have a complexity between these two bounds. Okay? And from a point of view of algorithm, this means that you don't care about what your algorithm may output when a two distributions satisfying this, this condition will happen. We only care what happens when they are equal or far apart. Okay, and today I will consider mostly the case where epsilon is a constant. When epsilon is not a constant, we have to take care about the value of epsilon in the complexity. But today I will not focus on that because my main purpose is to describe the complexity in terms of n and not of epsilon. So you can think of epsilon as being 1 over 100 or something similar, a very small constant. Okay, so the L2 norm version is actually fairly easy to analyze, and the sample complexity is constant. It's easy to show that with a constant number of samples of P and Q, you get enough information to decide whether the two distributions are the same or far apart with respect to a L2 norm. You can do this with high probability, with a constant number of samples. And more precisely, if you want the complexity dependence in epsilon, this is this one, 1 over epsilon squared. And this is a fairly folklore fact, but it has been proved explicitly, especially at the lower bound in that paper, 2014. So now, the L1 norm version is much more interesting, especially because the sample complexity is actually a very interesting value, n to the 2/3. an intriguing value, exponent 2/3 here. And so we have an upper bound and a lower bound. And actually, the lower bound is even stronger than that. It says that you need n to the 2/3 samples from P and also the same number of samples from Q. Okay. And so the upper bound was proved here by Batu, Fortnow, Rubinfeld, Smith, and White in 2000, using a very beautiful argument. And in that paper, they also gave a sketch of a matching lower bound, but it happened that making the sketch precise was extremely difficult, and it took 8 years until Vaillant proved the matching lower bound. Okay, and here I write n to the 2/3 because I'm assuming that epsilon is constant here. If you really want to have the dependence on epsilon here, it requires more works. And it has been done very recently by these guys, and the best bound is 2016. So now we have tight bands. We even know the exact dependence on the parameter epsilon. Okay, so let me try to give you some rough intuition about this n to the 2/3. Why do you need n to the 2/3 samples? Actually, the hardest case, the case which is used to prove the lower bound, is this case. So distinguishing between the upper situation here and the lower situation. So let me describe precisely this. So in the upper situation, so here we have this n to the 2/3 elements, each appearing with this complexity. So this means that the weight, the probability mass of this region here is exactly 1/2. Here you have n to the over 4, each appearing with this. So here it's 1/2 also, the mass. So what you get is a probability distribution, because the L1 norm is 1. And in the upper case, for Q, we take exactly the same. Okay, so of course, Q is equal to P, so we are satisfying it's a yes instance for a problem. And for the lower situation, we are taking the same distribution for P, but for Q, what we are doing, we are taking the same part. The blue part is exactly the same, but the purple part is similar, but with a completely disjoint support. So which means that the distance between the two distributions is exactly 1/2, because they agree on a fraction weight, the weight of the element for which it agrees is exactly 1/2. They disagree on 1/2. So it's exactly 1. Okay, and I'm claiming that distinguishing between these two cases requires n to the 2/3 samples. And proving this is fairly difficult. A lot of technical lemmas and insights are needed, but the main idea is that when you receive samples from P and Q, you will never be able to identify whether your samples come from the blue zone or the yellow zone, unless you have more than n to the 2/3 sample. Because if you have less than n to the 2/3 sample, with high probability, you will never obtain two same elements from the blue zone. So the elements, you will never be able to know whether they come from the blue part or the yellow part. And then you will never be able to distinguish the upper situation here and the lower situation here. Okay, so this is the first intuition about why this n to the 2/3 complexity is obtained, and especially why this lower bound holds. Okay. Okay, so n to the 2/3, classical. So now I consider the quantum version. And this has been studied in prior works, and the conclusion is so first, for the L2 norm version, you can do better. Instead of 1/epsilon², you can get 1/epsilon if you count the number of quantum samples. And for this L1 norm version also, you can get an improvement. You have square root n quantum samples, which are enough. Classically n to the 2/3, quantumly square root n is enough. So you get a not a quadratic, but a polynomial improvement. Okay, and here precisely a quadratic improvement if you look the dependence in epsilon. So good. But what is a quantum sample? So it's a delicate notion. There are several possible versions and variants of the concept of quantum samples. And the standard one is essentially that one sample from P means one copy of the state. Okay. And I will be a little bit more precise because this is, you need something a little bit stronger. So I will write what you need. You need a unitary U such that when you apply U on ket 0, you get the state I wrote. And you also need access to the inverse of the matrix. So when I say one copy, one sample, I mean one access to this unitary that construct this superposition from the all zero state, or one access to the inverse. I also count this like one query. So I assume that I have such a unitary that I can call for P and a similar unitary for Q. And I define that as one quantum sample. And then I can show that with square root n quantum samples, you can solve the first problem, and with n over epsilon quantum samples, you can solve the second. Okay. So now there is, of course, some criticism or concern here is that it does not really look fair to compare classical and quantum learning theories, and especially quantum and classical distribution testing, because the concept of quantum samples looks much stronger. So classically, you assume that you have one sample, which is one element, but quantumly, you have a superposition on all the elements, according to the probability distribution here as an amplitude. And even more than that, you have a unitary making this and access to the inverse. So it looks much stronger, and so not fair to compare the classical version with the quantum version. Okay, it makes sense, of course, when you have a concrete procedure to compute your, to produce your samples classically. Then if you can convert this procedure into quantum procedure and input a superposition, then you will get as an output a superposition like that. So it can make sense in such a situation. But for all the other situations where your samples really come from the outside, you don't know anything about the distribution, you only receive some samples, there's a big difference between having classical samples and quantum samples. And the main conceptual contribution of our work is a study of quantum distribution testing with classical samples. Okay? And I need to explain how this is possible, because it's not possible if you consider the query complexity setting. And to do this, we need to consider a slightly different setting that has been actually introduced very recently in 2019, which is considering distribution testing in the communication complexity setting. So there was a few talks about communication complexities. Professor Nishimura in particular discussed that. So we have two-party communication complexity. So here I'm talking about the classical version. And we assume that Alice receives as input T samples, T classical samples from P, and Bob T classical samples from Q. Okay, and they can talk. And I'm asking how many bits of communication do Alice and Bob need to exchange in order to solve the problem? That is this problem. Okay, And of course, nothing can be done if you have less than n to the 2/3 sample, because n to the 2/3 is the information theoretical lower bound, the number of samples needed to identify the distribution. So if you have less than n to the 2/3, the samples are not representative of your distributions and you cannot do anything. The trivial protocol will be Alice sends all samples to Bob. And this solves the problem if you have more than n to the 2/3 samples. And what is the cost? Well, each sample is one element from 1 to n, so it can be encoded using log n bits. The total communication is t times log n bits. And Andoni Malkin Nozatsky showed that actually you can do better if t is larger than n to the 2/3. Okay, so they obtained this bound. Okay, so maybe you're not familiar with this notation. So this means, this notation here means, the tilde here means that I ignore all the log n terms. So for example, the complexity here, the real complexity, if you consider everything, should be n over t square log n. But I don't want to write the log n because I don't care much about the log n, so I'm using this convenient notation. Okay. So now, so you see, so if t is equal to close to n to the 2/3, to the lower bound here, then what we obtain here is n to the 1/3 square, so n to the 2/3. So the same complexity as a trivial protocol. But if t is larger, so for example, t very close to n, then this becomes much smaller. And if t is very close to n, this becomes essentially constant. This means that we have a much better protocol than the trivial protocol when we have a lot of samples. And this is because when we have a lot of samples, Alice and Bob can locally learn from themselves a good approximation of P and Q and use this good approximation to, instead of the original distribution, in order to check whether the original distribution are equal or far apart, using a lot of standard techniques, linear sketching of distribution and so on. If you have a lot of information about your distribution, you can do clever things. Okay, so if you have much more than the threshold, the information theoretical threshold of n to 3rd, you can do very non-trivial things and obtain fast protocols. Okay, so this is a classical setting. And what we do, we consider the same setting, except that we allow Alice and Bob to use quantum communication. So all the samples are classical. Classical samples here and classical samples here. And only the communication is quantum. And we show that you obtain a quadratic improvement here. You can reduce quadratically the communication needed if P and Q satisfy this condition. So we have, unfortunately, one condition here for that lower bound, for that upper bound to hold, which is that P and Q have norm, at least the minimum of the two norms of P and Q are T over N. Okay, so the distribution are low norm, have low norm. So under this assumption, you can obtain a quadratic improvement over this lower bound. And we show also that it is tight. And this bound is tight. It's even tight under this condition. Okay, so under this condition, we can really show that you have a quadratic gap between the two. Of course, and I will come back to this later, the main open question is whether you can prove the same without this condition. It may be true, but currently we are not able to prove that. Okay, so this ends the first part of my talk with the definition of the problem and rough presentation of the result. So if there is any question, it's maybe a good time to ask.
All right, thank you. So please, any question?
So could you show me your quantum setting? You consider how to say distinguish the quantum states, root P and root Q, something. So
I'm not sure I understand the question. The quantum setting is written here.
yes, but yes, this is quantum classical, but do you consider some initial state is quantum state or not?
The initial state, what do you mean by initial state?
Root B or root Q. You consider root B, root Q.
No.
You don't consider that setting.
Yes. So
Okay.
that's the point. I said that setting is a little bit strange because we are comparing classical and quantum samples. They are not the same. So in this new setting, all the samples are classical, purely classical. But I allow quantum communication.
No, okay. Of course, this is more natural. So this side is not quantum.
Yes.
Not the distributed testing. This side is pure state testing.
It's yes, it's a pure state testing, and of course, it's a nice question. Of course, you can generalize this maybe later to testing quantum state and so on. I will have a small discussion about that about the very, very end of the last slide of the talk. But currently, the distribution are classical, the input are classical, and the output is classical because it's 0 or 1. You have to decide if they are close or not. The only thing that is allowed to be quantum is a communication between a symbol.
And also, I have another comment. So in the quantum information theory, they also consider this kind of problem. They consider some testing problem.
Yes.
With respect to distribution, but mainly they are considering the independence, and also they fix the size of or cardinality of each distribution.
Yes.
They increase the number of copies somehow, and their setting is somehow not symmetric. They consider two hypotheses about first error probability and second error probability is not equally discussed, similar to the Stein's lemma. And also they consider that the communication rate is 0 rate.
Mm.
That case is very actively discussed.
Yes.
Also, problem setting is completely somehow different. But
yes.
That kind of setting is very advantageous for the community of information theory.
Yes. I'm pretty sure I would also go back to that at the end. There are a lot of relation with information theory and all that. The difference is a little bit of problem setting and also the way we consider the complexity. Here, I really want the complexity in terms of n, which is the size of the universe for the probability distribution, which may be different from what, it's not really the rate, the number of bits sent. It's a little bit maybe different, but they are very related. Yes, I agree.
Yeah, I have a question. So in this related to Google's random circuit sampling, is also an important task to distinguish between the sample coming out of the superconducting qubits and the actual probability. And in the case of random circuit sampling, Google proposed to use the so-called linear cross entropy. Mm-hmm. So yes. So I just wonder if maybe that problem is a subset of this problem. So here you are considering kind of a two very general distribution. In the case of random circuit sampling, so we are comparing the distribution, whether the certain distribution follows the Porter-Thomas distribution or a kind of particular Porter-Thomas distribution. So I just wonder if you can think about whether this can be connected or how this problem can be connected together. So it would be very interesting.
It's a good question. Yes. So actually, what we are considering here is we want to design a protocol that works for any possible distributions. Okay, so we have maybe these assumptions and so on. But if you restrict yourself to specific distributions, then it's maybe possible to do it much, much faster.
Right, because in the case of random circuit sampling, the concept probability is kind of vague because each sample you would only occurs once.
Mm-hmm.
So it's difficult to get two bit string the same. So therefore, how to define the probability. So you can only approximate the probability by 1 over k, where k is like the number of samples that you have achieved. So yeah, that is the situation. So
mm-hmm. Yeah. Okay, so it's maybe indeed possible to design specific protocols for much faster than this for
right.
Specific, if you know that your distribution is from a specific class.
Yeah, actually, in the case of quantum random circuit sampling, it's like, so in the experiment, so for each experimental bit string that you obtained from the superconducting qubits, you go to calculate the corresponding probability.
Mm-hmm.
So therefore, one of the probability is kind of mathematical, another is like the experimental. So you're comparing the two. I see. Okay, thanks. Any other question?
Could you go back to the slide?
Which one?
Quantum sample complexity.
Sample complexity, this one. Yes.
This you explain the one sample means applying U and U inverse.
Yes.
How about without U inverse?
The question is, why do we need the U inverse, maybe?
Yes.
I think it's especially for this one. It's because you are using quantum amplitude.
So my question is, how about the complexity without?
Without. It's a good question. If you don't have the inverse, I don't think that you obtain an improvement here. But I don't know, I don't think we can prove it. We know any lower bound.
Oh.
Yes.
Can I ask a follow-up question? So have you thought about giving it a kind of phase factor, relative phase factor for each I?
Mm-hmm. So what do you mean by the phase factor?
Well, now it's like you're comparing two quantum states that has all real coefficients in superposition. I'm just wondering if it's possible to speed up if you for each state you give it a phase factor for each I.
Mm-hmm.
So if you give it a phase factor, would it make a difference? I think at least for if you calculate fidelity between the two states, you get a different values for sure.
I don't know. It's maybe possible to obtain something better if you have a phase factor. It may also make things worse, depending. I'm not sure what happens. There are several variants that you can consider. A very popular variant is to add some garbage here, which makes the problem more complicated, actually. But you can show that even with a garbage, you can do the same, obtain the same. If you have a phase factor, maybe it's helpful or it can be harmful. It may depend on the setting. But I don't think this has been really studied so far.
Okay, thank you. Any more questions?
Oh, I have one question. So in the L1 norm case of this classical and quantum case, you write this complexity with epsilon constant, and when epsilon is not constant, is it the same as the L2 norm case? So it increases as epsilon decreases, like 1 over epsilon or something?
Yes, it's 1 over epsilon to the power, I think 2.5 or something like that.
Ah, yeah.
Yes, 2 or 2.5, yes. Yeah.
Okay, okay. All right, thank you.
And yes, so precisely here you will have, I think, well, I can write it here, you will have a big O of n over t epsilon square. And here you will have a big O of n over, well, actually, this one square.
Yeah.
You still have exactly quadratic improvement here, even if you take the epsilon in consideration.
Okay, I see. Okay, thank you.
Okay.
Okay, maybe we should move on. So until the end, we can, discuss again. Yeah.
Yeah. Okay. Okay, so now I will go through some details about how to prove that. So the key idea, even for the classical protocol, is a notion of occurrence vector. So, so consider T samples of the distribution P. And for each I call xi the number of samples corresponding to I. And I collect all these xi together, this gives you a vector, and I call this vector the occurrence vector of the sample. So for example, here I have n equals 5 and 6 samples. So 1 occurs twice, so I have a 2 here, 2 occur once, 3 occur twice, 4 0 time, and 5 1, so I have this vector. Okay, so I represent the number of occurrences in my samples as a vector. And a theorem, I write it in an informal way, but a very important theorem from that paper say that if you call x the occurrence vector of the samples of P and y the occurrence vector of the sample of Q, then when T is large enough, so larger than the threshold, information theoretic threshold, and when P and Q have small enough norm, then with high probability, a good approximation of the L2 norm of the difference of x and y gives a good approximation of this, the difference of the L2 norm of P minus Q. So that really says that the occurrence vector are a good indicator of the distance of the original distribution. Okay, and so how to use this technique for a case? We use the crucial observation that to decide whether this or this hold, it's enough to decide whether this or this hold. Because, so it's a very trivial observation. So if you have, of course, P minus Q1 equals 0, then this means that P minus Q2 equals 0, of course, because P is equal to 2. And if you have P minus Q1, which is larger than epsilon, then you have P minus Q2, which is larger than epsilon over square root n, due to the Cauchy-Schwarz inequality. So if you are able to detect with this is the case and this is the case, you are able to solve the original problem. Okay? So this reduces the problem of estimating the distance, the L1 distance, the problem of estimating the L2 distance, which a much smaller value here. And we will use that. Okay, so this is the protocol. So it's from our paper, but the protocol is the same protocol as AMN, rewritten for the special case we are considering, the case of P and Q of low norm. Okay, so you first take alpha, and alpha, I wrote it here, but if you don't care about epsilon, you can consider as alpha of order of T over N. And the first step here, simply check whether P and Q are close in norm, are the same norm. If it is not, we know that they are far apart. So we give up. We know that they are far. Okay. And otherwise, what we do, we simply approximate that, the difference, the norm, L2 norm of the difference of the occurrence vector. You obtain a good approximation of it using standard techniques. More precisely, what we call a 1 plus epsilon approximation. I will explain this in the next slide. And with standard techniques, this can be done with a complexity 1 over alpha squared, which gives you this. Okay, so that's why we get the complexity I claimed in the previous slides. And then once you have delta, you only need to check whether delta is small or large. If it is very small, then this will show that P is equal to Q. If it is large, it will be this proof that distance between P and Q is large. And more precisely, this is done by comparing it with this threshold, this value of the threshold. So I don't explain how do you get this threshold, but the point is that, as proved in their paper, when the norm of the P and Q is fairly small, then this protocol correctly distinguishes between the two cases, P equal Q and P and Q far in the L1. Okay? Because delta is a good approximation of the L2 norm, and thus a good approximation of the L1 norm. And remember, for Anthony, Malkin, and Ozaki, they didn't have any assumption of the norm of P and Q. This is because when the norm of P and Q is large, they are able to do some pre-processing step that will convert the distribution into distribution with smaller norm while keeping the distance. So they first do the pre-processing and then they apply this protocol. So this gives you the complexity. This complexity, the dominant step is this one. So this complexity. Okay, the pre-processing has this cost, which is the same as this. Okay? And the quantum case is actually, the protocol is exactly the same, except that now for computing the approximation of the delta, I use a quantum protocol. And classically, it requires, the complexity was 1 over alpha square qubits of communication. And with our quantum protocol, it's 1 over epsilon, it's 1 over alpha qubits. So you obtain quadratic improvement. And otherwise, it's exactly the same. So the theorem is also true. And what we get is an algorithm that solves the problem when the norm of P and Q is small enough, with the complexity n over t. No, it's n over t instead of n squared over t squared. But the point is that we cannot obtain, currently we cannot obtain a general result for any P and Q because the pre-processing step used in the classical case cost a lot of communication, n over 2 squared bits of communication. And we don't know how to speed up this part using quantum communication. Okay, so we cannot use this. So we cannot remove the assumption that the norm of P and Q is small. Okay. So let me explain a little bit how to compute an approximation of that faster in the quantum setting. So first, what do I mean by an approximation? A 1 plus epsilon approximation means a number which is between 1 minus alpha this thing and 1 plus alpha this thing. This is what I call a 1 plus alpha approximation of this quantity. And there should be a square here because I square. I forgot this, but there is a square here and a square here. Okay. And the idea is to use a very powerful technique called the RMS technique, the by Alan Matthias Szegedi. So it's a very famous paper. That paper received the Gödel Prize, which is the highest prize for one paper published in theoretical computer science. They received it in 2005, I think. And so the idea is fairly easy. It's use the hash functions. Okay, so a set of functions called hash functions from this set to this, which are four-wise independent. Four-wise independent means that for any four pairs, x, y, like this, where the x are from 1 to n and y minus 1 and 1, the probability that this event and this event and this event and this event, the four events all simultaneously, is 1 over 16, which will be exactly the probability if h was a completely random function. Okay, so h behaves like a random function, at least when you look at four pairs, x, y. It's what we call four-wise independent. And we know that they are easy to construct. Okay, and then consider fi equals this thing. Okay, so the sum for the h, it's an I here, hij, time xj minus yj, and you take the square. And now my claim is that when I is taken uniformly at random, the expectation of this value is exactly what we want to compute. Okay, the square of the norm of x minus 1. And the variance is essentially the square of this quantity. And the proof of that, it's only calculation, but I can do it very easily. So if you compute that, the expectation of this value, you will expand that, the product, and what you get is term like that. And you see, for example, for the first term, x1 minus y1 squared, what you get is hi1 squared, which is 1, because hi1 is either 1 or minus 1. In both cases, the square is equal to 1. But here, for the next term, when you have x, you have a 1 here and 2 here, it will be hi1, h1, 2. And hi1 and hi2 are both with probability 1/2 1 and probability 1/2 2. Sorry, 1/2 minus 1. So it will be minus 1 or 1, the product, each with probability 1/2. So on average, it will be 0. So this term will disappear. And what will remain is exactly this quantity. And for the variance, you have a similar calculation, much more complicated, but you can show this above. Okay? So you have an estimator, fi. You know that the expectation of the estimator is exactly what we want to compute. And the variance is superbounded by twice the square of this value. Okay, so then to obtain a good approximation of it, a 1 plus epsilon approximation, is very easy. You take 1 over alpha square values of I, okay, and you output the mean of fi among all these values. And you can show that this will be, with high probability, a 1 plus epsilon approximation of the variance. The standard technique using the Chebyshev inequality and so on. And in the quantum setting, you can use a very nice result by Montanaro based on quantum amplitude estimation that shows that for this kind of problem, you can obtain a quadratic speedup in the quantum case. Okay, and so you can compute a similar 1 plus epsilon approximation using only 1 over alpha called to the function f. Okay, but I need to define what is a call to f. Okay. A call to f means, in the quantum setting, implementing this operation. In a unitary way, so constructing in that way. So that if you should be able to apply this operation on superposition. And you also need the inverse. So if you are able to do this, then you can apply this method. And the cost will be 1 over alpha calls to this operation. And I'm claiming that this operation can be implemented in log n bits of communication between Alice and Bob, because Alice has x and Bob has y, and because you have a linearity here, it's xj minus yj. Okay, so you have to think a little bit to understand that, but it's not very difficult. Okay, so to conclude, we are using essentially the same, almost the same protocol in the classical way, except that we use a quantum protocol for obtaining an approximation of this delta. Okay. So we obtain, finally, the complexity of the approximation is that. So we obtain this complexity because this is a dominant term in the algorithm. The step 3 is the most, the step that costs the most communication. Okay, so to summarize the results, so we obtain a quadratic improvement for when you have P and Q have small enough norm. Okay, so conclusion of the whole talk. So we studied again this problem, closeness testing in the L1 norm version, deciding if P is equal to Q or the distance between P and Q is at least epsilon. And we studied that in the communication complexity setting. And the main conclusion is that when the distribution of small norm, there is a quadratic gap between classical and quantum communication complexity. And actually, our quantum protocol is optimal. We can prove a matching lower bound by a reduction from the gap Hamming distance. And to do this, you need a version of the pattern matrix method tailored for partial functions. It's a little bit technical, so I completely omit this part, the lower bound, from this talk. But we can prove that we cannot do better than our protocol when the distribution has low norm. And the nice thing, again, is that we are working in the setting where the samples are classical samples. On the communication is quantum. So this shows quantum advantage, quantum supremacy for quantum learning theory with classical samples. We don't require quantum samples to establish this quantum supremacy. And of course, the main question is, can we get the quantum advantage when the distributions have large norm? I don't know, we don't know. It's really an open question. And a few interesting research directions. So the first one, secure protocol. So in their paper, Andoni, Malkin, Novaski, they show how to convert their protocol into a secure protocol. Secure protocol means, like in the talk by Professor Nishimura, the player cannot get any information about the distribution except what they know from their input and what they know from their output. And they show that their protocol can be converted to have this property. So one question is, can we do the same for our quantum protocol? The second thing is consider, of course, other properties. For example, in that paper, same paper considered independence testing. So this time you have only one probability distribution and you have three samples, okay? But the probability distribution is of this form. The samples consist of two parts. And you are giving the first part to Alice, second part to Bob for each sample. And you ask if P is a product distribution or far from any product distribution in some sense. Okay, so we can consider if quantum helps for this problem. I believe this is true, but we need to work that. Another thing is closeness testing for other norms. Okay, so we studied the case of the L2 norm, the L1 norm. We saw that there is a big difference between the complexity. L2 norm is very easy, L1 norm very difficult. So you can ask for the complexity for P, say from 1 to n. If there is a smooth increase in the complexity or is there a sharp thing? So I think it's an interesting question. And finally, you can think of quantum properties. So for example, a very rough example, I haven't really thought much about that, but you can assume that Alice and Bob get the copies of a quantum state and they want to decide whether it's a product state or far from a product state. Okay, and how, what is the amount of communication you need in order to do that? It's very connected to quantum information theory, but I don't believe that it has been studied explicitly in that setting when you consider the communication complexity. Okay, thank you. If you have any questions, please.
Thank you. So we can take more questions now.
Do you expect some advantage when we use the prior entanglement between the Alice and Bob?
I don't expect for classical problems in that setting.
Yeah.
Because, I mean, we almost, I don't think we know any, beside the super dense coding in that setting where you have Alice and Bob, and they want to solve a classical problem with classical input, classical output.
Yeah.
We don't have any good example where you can do, where prior entanglement helps. I don't expect for that setting.
Yeah.
We can have if you have more than three players, for example. Or SMP, like Professor Nishimura did with a 3-player and a referee, then you can have. Or you may have if you consider quantum problem, quantum input, quantum output.
Yeah.
For the basic one, I don't believe that quantum, the entanglement helps.
Okay. Yes. Thank you.
Hello? Can I ask a question?
Sure.
You already consider only P equal Q or P and Q is far.
Yes.
How about the P equal Q, P and Q close or far? In this case, any study is.
Yes, it's a very nice question. Yes, of course, it's one of the most natural questions. Yes, yes. So as you said, that we consider exactly equal or far.
Yeah.
Another version is to consider the case where here you have the distance P minus Q, which is smaller than some delta.
Yeah.
The small delta. Yes, and the point is that for this version, the problem becomes very difficult.
Yeah.
At least classically, we can show that you need n samples. Okay, I'm not sure if there is a classical, if there's a quantum lower bound. I think there is also a strong quantum lower bound for this case. But the point is that there is a big difference in the complexity of the problem here. But for this one, the L2 norm version, actually, these bounds also work for the version with an epsilon, with a delta here. Because the algorithm here simply estimate, they don't really do something very clever. They estimate the distance. So you don't really care about its equality or not. You really need to have a gap between the delta here and the epsilon here. For L2 norm, it's robust, but for L1, it's not. It's really required on the fact that you have an equality.
How about in your case?
In my for the communication complexities, I think I haven't really thought so much, but typically the lower bound for query complexity can be also mapped to the communication complexity. So I believe that's the same situation. Yes, if you really want this version, you cannot do much in communication complexity. At least classically, you cannot do anything, and quantumly probably you cannot do anything clever.
Thank you.
More questions? Do we have some requirements on the success probability?
Yes, we do have some. Yes, so if you want, yes, so you will have the. See, if you want the success probability larger than 1 over the delta, then the complexity will be this n over t, and you will have a time log 1 over delta. So you can have precise description of the complexity involving the error you want. And the point is that the dependence in the error is extremely good. So you can have whatever success probability you want.
So this is a general rule.
This is essentially general rule because when you have something that succeeds with probability larger than 2/3, then you can amplify the probability. Because it's one-sided, especially in our case, it's one-sided error. So you can amplify things. Yeah. So success probability is not a big issue here, but it's not probability 1. It's of course with high probability you can make the probability as large as you want with a very small cost, but it's not exactly.
Okay, thank you.
Can I ask one more question?
Sure.
Yes.
Yes. Maybe I might have misunderstood, but I thought that your large delta considers the distance between the occurrence vectors. Is it right?
Yes.
But this occurrence vector doesn't have full information of the distribution. But even if the distributions are different, even if the distributions are different, the occurrence vector x and y can be the same.
Yes.
I thought so. Intuitively, it's a little bit difficult to understand intuitively how this evaluation of large delta can lead to the similarity of the P and Q.
Yes. So the point is that when T is very large,
yeah,
larger than that, it will be some kind of faithful representation of the probability. But you really need this assumption.
Yes, T
is
really large.
It's completely random and doesn't give you anything.
Sorry, what was the T in here? So a sample, number of samples. Yes.
Small samples doesn't give you any faithful representation of the distribution, so you cannot do anything.
Yeah.
But when it's larger, this gives you some information. So it's there's a correlation between the X and the P.
Yes.
And the difference are also related, and by making some calculation, you can show a good approximation of one, give you good approximation for the other. But
yes.
For this to be true, you need a technical condition, which is that the norm of P and Q are small enough.
Yeah.
It's not trivial. This theorem, I say informal, but it's not trivial at all. It requires this technical condition.
Yes, I see. So the most important part was that T is sufficiently large.
Yes, exactly.
Yeah. Yes. Okay. Maybe the similar techniques related to the occurrence vector have been studied in the information theory, which is called a method of types. And so maybe asymptotically it works a little similarly, I think.
Yeah,
but,
yes.
Yeah, your works are.
I mean, the occurrence vector is essentially the only thing you know about the representation. It's what, from your sample, the only thing you can use is the number of occurrence of each element.
Oh, yes, that's true, yes.
So you can probably explain all the known methods using only occurrence vectors. I think.
Yeah. Thank you very much.
All right, any further question? If not,